And now let's move on to the dipolar Hamiltonian. It's a spin-spin interaction, and here we are not doing the same thing that we did before by starting by the general expression, but we already look at the expression for the dipolar Hamiltonian in the laboratory frame, and it's given by the formula that you see here. You have mu0 divided by 4 times p, and now comes in this very famous r to the power of 3, the distance between the two spins to the power of 3. We will quickly talk about this later, times the product of the gyromagnetic ratios, times a whole series of letters which we call the dipolar alphabet. And the dipolar alphabet, you see the full expressions here on the bottom, they actually take into account your orientation dependence of your dipolar coupling interaction, so the orientation of your bond relative to, not the bond, but the distance between your spins relative to the external magnetic field. And the second thing is that they collect all our spin operators that are relevant. You can imagine that this laboratory frame expression for our dipolar coupling is rather complicated, it's rather long. So again, what do? We want to move into an interaction frame as we did before for our chemical shift Hamiltonian, and we want to see which terms can we drop thanks to the secular approximations. So the only question is now, if we move into an interaction frame, so in one that is going to rotate along the z-axis with the Larmor frequency, which of all of these dipolar alphabet terms will pick up time dependencies, and which of those can we then actually drop. Now let's look a bit about the individual expressions, and let's think about this a bit closer, a bit deeper. If we look at the E term, for example, we have an I plus and we have an I plus operator. What happens is when you move into an interaction frame, and both of these are going to pick up time dependencies with the Larmor frequencies, you're going to rotate at twice the Larmor frequency, and then you can for sure drop the E term. And the same is true for the F term, where you have twice the I minus operator, so you will rotate with a minus 2 omega 0, and then again in the interaction frame, thanks to the secular approximation, you can drop the F term. In the C and the D term, you have once the IZ operators. These, as we said, they will not pick up a time dependence because they are already oriented along the z-axis. So if the whole coordinate system now starts moving along the around the z-axis, they are unaffected. So they will not pick up a time dependence, but the I plus and the I minus terms will, and that's why we can again say we drop the C and the D terms completely. The situation looks different for the A term, because the A term, it contains two IZ operators. Both IZ operators for both spins will not be affected by our interaction frame transformation. They will not pick up a time dependence, so we have to keep them as secular term. So you can see we can drop most of the Hamiltonian from C to F. We keep the A part, and now the only tricky thing is thinking about what happens with our B term in our dipolar alphabet. Because the B term is a bit tricky. Why? Because it is composed of flip-flop terms. You have an I plus, you have an I minus, and the net effect is what we call a flip-flop in NMR. And what is interesting is that we have to do a case distinction here. Because if you have a homonuclear dipolar coupling, so when the two spins have the same Larmor frequency, what is happening with these flip-flop terms? Well, you pick up a plus omega 0 from the I plus that goes into the interaction frame, but you will pick up a time dependence with minus omega 0 because of the I minus operator for the second spin. Getting this time dependence. And so you have a rotation with a plus omega 0, you have a counter rotation with a minus omega 0, and the two rotations will compensate each other in the homonuclear system. And so that's why for a homonuclear two-spin system, our homonuclear dipolar interaction will not have a time-dependent B term in the secular in the interaction frame, and this is why we have to keep it in our final expression when we already applied our secular approximation. And this was only true because they had the same Larmor frequency. But if you now look at a heteronuclear spin system, so where the two Larmor frequencies are different, for the two spins. Then the I plus operator will pick up a time dependence plus omega 0 of one nucleus, and the other one will pick up a minus omega 0 from the other nucleus, but the two nuclei don't have the same Larmor frequency, and that's why the plus omega 0 and the minus omega 0 rotations will not fully compensate each other, meaning that there's going to be in the interaction frame a residual time dependence left. What does this mean when we have a residual time dependence and we want to apply our secular approximation? Well, we can just drop it, meaning that in a heteronuclear spin system we can completely drop the B term and the A term is the only thing that remains in our expression for the dipole coupling in the interaction frame. And here in the last slide we actually want to see what is the effect of the presence of a dipole coupling between two spins on the energy levels. And if we, as we saw, when we have only one spin, one half, and we put it into a magnetic field, and we only consider the Zeeman interaction, the chemical shift Hamiltonian, then we will just get two energy levels and one transition. But as soon as you have two spins that are coupled with each other, you start getting four energy levels, as you can see here, and all of these energy levels will lead to different transition frequency because the energy differences and therefore the frequencies of the transitions are different for all of these, amongst all of these different energy levels. And what is important is that you have a full variety of transitions that could be possible. You have so-called single quantum transitions, those where our magnetic quantum number changes by 1. So what would this be? For example, it would be a transition from the alpha-beta to the beta-beta state, because then you just have one alpha, so one spin one up, that is going to be flipped to a spin down. This changes your total magnetic number m just by 1. But you can also have double quantum transitions, for example, when you have from an alpha to a beta-beta state. There you actually change both spin ups to spin downs. This changes your magnetic quantum number by 2. And you can also have zero quantum transitions, and zero quantum transitions are interesting because they are from an alpha-beta to a beta-alpha term, and this means that you have a flip-flop actually of your states. What was up goes down and what was down goes up, and this actually creates net a zero difference in your magnetic quantum number. And there is a whole theory behind which transitions are allowed and which are not. So this has to deal with which transitions actually are expected to have zero intensity. The summary of all of this is that in principle you can only observe transitions that have a delta m equals of 1. So you can only observe the single quantum transitions when you just excite normally. And this is what's actually, you see it here, from all these different transitions that we could have, the only ones that are really going to be observed after the 4 transitions related to our single quantum transitions in our system. Final remarks also on this slide. When we look at our spectrum with our 4 possible transitions, well, this is depicted in what we call a weak coupling regime, and a weak coupling regime is where actually the chemical shift difference is bigger than the strength of our dipole coupling. Why is this important? Because actually you can have a smaller number of lines if the coupling gets much stronger compared to our chemical shift difference. So when you start moving into a strong coupling regime, these 4 individual lines start overlapping. You cannot really associate which line belongs to which one, to which spin, and then everything starts overlapping and everything starts becoming a bit more complicated. And the second remark is, of course, about the famous 1 over r to the power of 3 dependence of your dipole coupling. On what does the dipole coupling depend? Well, as we saw from the previous expression, first of all, it depends on the gamma, on the multiplication of the gyromagnetic ratios. So the higher the gyromagnetic ratio, the higher your dipole couplings. That's why homonuclear dipole couplings between protons are much bigger than homonuclear dipole couplings between carbon. This will be very important for magic angle spinning, but we will get there. The really very important thing that you need to remember about the dependencies of the strength of your dipole coupling is the distance between the two spins. The closer the spins get together, the more your dipole coupling actually explodes. And you can imagine that if you have distances close to 1 angstrom, that you will have a huge dipole coupling, and every small 0.1 angstrom that you're moving closer will make, thanks to this 1/r to the power of 3 dependence, will make the dipole coupling even bigger. So you can really imagine that the dipole coupling is very sensitive to structural information, and that's why actually the dipole coupling is of so much importance in structural characterization of molecules. This concludes our discussion of Hamiltonians in general, and now we will move closer and closer to our actual final goal, as we said, discuss Hamiltonians under the effect of magic angle spinning. And what we're going to do in the next video is to really see about what is the importance of rotations in the theoretical treatment of Hamiltonians. So thanks a lot for being with me today. You can find the video link to the next video here on the side, and I hope to see you next time, of course. So until then, ciao!